Okay, for my EECS 435 final project, I wanted to do an investigation into generative adversarial neural networks. To structure the project, I broke it down into two main parts. I did background on the content, which is part A. I did a part B of the frontier, where we discuss open problems and future work/research areas. Okay. So part A1 is the introduction. I just kind of explained my rationale for going through this. I actually became interested in GANs when working with Professor Doug Downey. He was the first to kind of propose the notion to me, and he brought up there kind of an advanced topic that you need to be a bit more nuanced to understand. So I thought that was made an appropriate topic for this course. In part A2, I explore the model GANs and kind of go through like a high-level description of how they operate. I think I'll just quote the loose analogy here is to think of a GAN as a game played between a counterfeiter and a bank clerk, where the counterfeiter is the generator neural network and the bank clerk is a discriminator. And the goal is for the counterfeiter to make the bank clerk accept fake money as real. I'll let you go through the actual formal description. I think it's pretty concise. There's a description of the actual whole architecture and also a summary at the bottom. For part A3, I go through an implementation. I adapted this from Eric Linder-Noren, which is really useful. So it's well commented. As you can see, you can run the code, which I think was useful. You select yes to train, choose a number of X. I'm just going to choose 20. Normally, you should choose on something on the order of magnitude of 10 to the 5. It takes a second to load. We'll start running. Well, that's running. Just to go through, it actually breaks down two methods where you build the discriminator network and build the generator network. As you can see, these are kind of arbitrarily chosen network sizes, and they're not really empirically derived. But it's cool. It just shows that one optimizer is used. We also see the discriminator. We see Z being set to generate the actual data samples, and the model being stacked. It should be running by now, yeah. And then 20 runs go. Okay, now we go into frontier. In the frontier, we explore 5 different topics. I'll go through them really quickly. We see non-convergence, and also these are all derived from tutorials and papers I'm reading. I'll go through that at the end. The main problem is non-convergence, right? So because GANs are pretty much a game played between two neural networks where their cost functions are zero-sum, it can be difficult to find the correct optimizer, and we don't necessarily convergence in the traditional sense. See mode collapse, where we don't generate good fake money. We generate like partial subsets. There was a really interesting conversation about the evaluation of the generator itself and how we actually empirically derive that, which seems to be one of the more pressing ones. There's also just discrete outputs, which is problematic, right? So say you want to mimic something that is discrete, we have the restriction on G of Z that it is in fact differentiable, so discrete outputs are a no-go. However, GANs would obviously be really valuable in something like NLP, right, if we were dealing with generation, perhaps. And then probably the most interesting restriction is this notion of unbalance, right, that we need the game to be fair between the bank clerk and the counterfeiter. This was a really interesting area and problem because there's some disagreement on whether it actually is a problem. But I think the intuitive notion is that it needs to be balanced, so you can't have one dominate the other. And then we go into future work and possible solutions. So this is really, really cool. I thought solving mode collapse seemed really problematic, and there's actually a particular type of a GAN called a manifold guided adversarial network, MGANs. And they have a subset. They have a sub-generator and discriminator that actually is designed to just rebuild G of Z and XG. And those, in essence, guide and help to alleviate the mode collapse problem. The mathematical implementation was tricky, and I struggled to read the paper, but I think it was really promising and worthwhile work. It's just cool when you have to evaluate G, and just going through different metrics and there were pros and cons and unbalance, right? So this is a good, I think the correct approach was to empirically derive balance between G and D, and so you actually just do cross-validation and try different little actual parameters for the network. This conclusion, overall, really through this project, I really thought it was great. Thank you for the opportunity. Thank you for a wonderful class.